Okay, so in this session, we are going to talk about the new concept of covariances and correlations. Let's say, if we are interested in a joint distribution, okay, so let's say that we have the mean and the median already. But if we have more than one variable, we are going to want to see the relationship between these two variables, okay? So we need, let's say, some measures. And one measure we are going to discuss is the covariance and the correlation. But the caveat here, okay, using the covariance and correlation only capture a particular type of dependence, namely the linear dependence, okay? So the definition, covariance of X is equal to this one. Equivalently, it is this one, okay? The first example. So we have this distribution and we wanted to find the correlation. So first we find the expectation of the X, okay? So the expectation of the X, we can integrate this and times X. We get 7/12. And by symmetry, we can get the EY because X and Y, okay? And for the covariances, okay, so we have to find, let's say, X, Y, okay, X, Y times together and times this one, there's a distribution. And here we use the lotus again, okay? And we get 1/144, which is positive. The correlation, it is very similar to the covariance, but we needed to divide by these two numbers times together. So the correlation is useful because it gets rid of the unit, okay? Because let's say if X is, let's say, the mate, right? The mate, and Y is the second, and this one is the meter times second, and it gets rid of the unit. It is unitless, okay? The correlation is unitless. But another property that is interesting is that the covariance is between -1 and 1. This is another interesting property also, okay? So we have to look at the Schwarz inequality first. That is this one, okay? So how do we prove the Schwarz inequality? Okay, so first we have to imagine, okay, imagine about this one. So this one, sin is square is greater than or equal to 0, okay? So first we can let's say separate this one into these three terms. Also this one, square, it must be non-negative, right? So we can separate into these three terms. And let the A be EV square root, be EU square root. It is imagine also, right? Imagine also. Separate this one. So EUV is greater than or equal to minus this one. Or in the other word, and we can get this one also. Okay. So by using these two magic formula, we can get this one. Okay. So the Cauchy-Schwarz, okay, the Cauchy-Schwarz says similar thing. This one. And the correlation between -1 and 1. So we can divide it into three categories, okay? If X and Y are positively correlated, rho XY is greater than 0. So we may want to visualize something like this. Okay? Something like this direction. X and Y are negatively correlated. If rho of X and Y is less than 0, we can imagine something like this one. Okay? And if X and Y are uncorrelated, if XY is equal to 0. So it may get something like this. spread around. Okay, but it may be some cases also that is x and y are, let's say, the quadratic relationship. But because in this side is negative, but in this side is positive. So on the net, if we wanted to capture only the linear dependence, we can say that, oh, it is uncorrelated. But is it the same as independent? No. Okay. That is the first property. If x and y are independent random variable with finite variances, so independence, okay, independence implies uncorrelated. But uncorrelated doesn't imply this way. Okay. Why? Because if it is independence, how do we calculate EXY? EXY is gonna be what? The double integral, right? XY, F, XY, dx, dy. But since it is independent, we can what? We can disintegrate this one. We can separate this one into two terms. X, Y, dx, hy, dx, dy. And finally, we are going to get EX times EY. Okay? But the opposite is not true. But the other direction is not true. Why? Suppose that random variable x can take only 3 values, okay? Let's say x can take only on, let's say, minus 1, 1, and 0. And each of these has the same probability. And y is equal to x squared. The parabola version that we talking about, okay? So it's gonna be this value and this value. So they are not independent. All right. Because what? Because they have the relationship like the parabola. However, E of xy is gonna be what? E of x to the power of 3. It is e to the x. It is 0. And ex times ey is equal to 0 because ex is 0. So the covariance is 0. Okay. So independence implies uncorrelated, but uncorrelated doesn't imply independence. The second property, suppose that x is a random variable with finite variance and y equal to ax plus b for some constants. If a greater than 0, low xy is equal to 1. If a less than 0, okay. So let's say we wanted to prove this one because the other one is very similar. What do we do? First, we find the correlation. E of xy is going to be what? Exy minus ex times ey is equal to what? Equal to e of ax squared plus bx minus e of x aex plus b. What does it mean? Aex squared plus bex minus aex squared minus bex. Because we have bx on the both sides, right? And how do we group this term? A ex squared minus e of x squared is gonna be what? A variance of x. A sigma x. But a sigma x. Oh, sorry, not okay. So we have sigma x here, but here it is sigma y. So the correlation a sigma x, and we have sigma y, sigma x is equal to 1. So if it is perfect linear relationship, that is the case when the correlation is equal to 1. The third property. So previously, we said that we can sum only variance of x and variance of, let's say, x and y are uncorrelated, right? We can sum the variance. Because in previous lesson, we talk only this, because we have not defined covariance yet. But now we have defined the covariance, so we get this term. How do we get this one? Let's say we want to find the variance of x plus y is equal to what? Is equal to e of x plus y squared minus, oh, okay, e x plus y squared. It is ex squared plus 2exy plus ey squared minus e of what? X plus square minus 2, let's say, exy. Okay. And minus what? Ey squared. Okay. Group this term. Ex squared minus e of x squared is gonna be what? Y raised of x. Group another term. Ey squared minus ey total in square. What does it mean? Variance of y. And we have the leftover term, that is this one. What is this? Plus 2 covariance of x and y. Okay. So if we are not sure that they are related or not, we can distribute the variance. Okay. But we have not forget this term. Okay. Do not forget this term. Next. It is similar, except that we talk about in the case of the n variables. We have variance of x and minus this one. Or let's say if we wanted to say the very concise notation is going to be covariance x I x j sigma all I and j. We can get this one. This one is shorter. Okay. Because what? Because if we consider covariance of xi and xi, it's going to be what? It's going to be e of xi squared minus exi squared. It's going to be variance of x. So covariance with itself, it is variance. That's why we can say in this notation. But if we want to find 2 in front of it, so we have to separate into these 2 terms. Okay. Optify is now uncorrelated. Surely the covariance 0. Okay, so in this lesson we have talked about the covariance and considerations, and in the next lesson we are going to see, let's say, one of the most important concepts in this lesson, which is the conditional expectation. So see you next time.